Hello, good evening, everyone.
Good evening, sir.
Yeah, okay. I hope you. If yeah, what happened? So you have confirmation. Okay. You. But have you gone through the lectures first place?
Yes, sir.
Okay. No, no. I'm okay. How many of you have issues in EM algorithm?
Me too, sir.
Huh? Everyone.
Sometime we stuck in the questions. I think the concept is clear. I think, but in questions we stuck. I mean, I
Okay. Questions if you're stuck, right? Okay, maybe I'll go through walk you through the slides possibly. We'll try to understand it. Why and like we'll try on like most important concepts which are useful for solving the questions. And anyway, today we are going to see the questions. So let us see like if that can be helpful, right?
okay, sir. Thank you. Sir.
Okay, maybe at least all of you know the Bayesian like not
Yes, sir.
Bayesian, the base
There's
theorem.
yes estimation all that. We
Yeah.
know.
So maybe we'll look at it once more.
Okay, sir.
Hmm? What is so generally what happens here is okay. First place, what is likelihood? That is very important, right? Why we use the likelihood methods and all. What are all those methods? Uh,
Maximum like we use likelihood and prior distribution and prior distribution like that things.
yeah,
We
all
use
of this
for the
like
estimation
why
of for the estimation of the parameter.
yeah parameter right of the unknown distribution. So
Yes, sir.
suppose you have some samples with you, right? And
Yes, sir.
based on that sample you wanted to say something about its distribution, right? So if you it just recall from your statistics background, what is the thing we know that there is one sample and there is another population, right?
Population.
Correct. So suppose you have some samples and that population can have any distribution, right?
Yes, sir.
And we have some known distributions with us, and generally we know that all of these distributions comes from, suppose if it is uh, coin toss example. So generally we know that okay, there is two outputs or outcomes. In that case we say that that will have the Bernoulli distribution, right?
Bernoulli distribution.
Likewise. One minute, I think you're having some noise in your background. If you can, it is
Oh,
possible.
sir.
If you possible,
Okay,
you
sir.
just go to some other place, right, where it is quiet. You can talk to me. That's not a problem. But if the noise will not be there, so it will be good. So all of you can actually engage into this conversation. That's probably will be good for us, right? Okay. So yeah, so we know that there is a sample, and for that sample, so that sample should be coming from some population, right?
Yes, sir.
And let us say if the population is unknown to you, what do you mean by population is unknown to you? Me is there is some distribution of a
We do
population.
not know the distribution of the population. I think.
Yeah, maybe we know the distribution, but we don't know how it behaves, and the behavior of the distribution depends on its parameters, right? So for example, Bernoulli distribution's behavior depends on its one parameter, which is
P.
p, which is the probability of success, right? If I talk about binomial distribution, there are two parameters, n and p.
N and P.
So suppose you have some samples and you wanted to say something about its distribution. That means you wanted to know about its parameters,
Parameter.
right? And given a sample, how what we can say about its parameters, right? That is the goal in this
To estimate.
parameter estimation techniques, right? And one of the parameter estimation technique is maximum
Maximum likelihood.
likelihood technique, right? Okay. So in that case, what we do is whatever sample is given to us, what we can do, we'll think about okay, we'll let us say if this is a sample, right? If this is an observed sample, I may say that this might be a binomial distribution, right? We are supposing that it's a binomial distribution, so it will have two parameters. Let us say. So how to find out its parameters is like given a sample. So okay, so in the slides, it is we think about this parameter as the Bernoulli distribution, right? And what we are saying is maybe it is a Bernoulli distribution with probability of success as p. So we have to find out its likelihood. What is the likelihood? Basically, likelihood is a uh, it's a product of
Product of I think
probabilities, right?
that probabilities which are given
Yeah.
for the function.
So that product will be a function of that parameter, right?
Yes, sir.
Fine. So if more than one parameters are there, in that case, what we have to do? We have to differentiate, or maybe in that maximum likelihood estimator
With
process,
respect to that, we differentiate
yeah, and others we treat, other parameters we
as a
treat
constant
constant, yeah, and then we solve that problem. That is our maximum likelihood estimate, right?
estimation.
So here in this case, what will be its likelihood? Let us say if I think about that, okay, maybe this is a, and okay, there are two more important assumptions. One is the IID assumption, right? Basically,
Independent and random.
these samples, or this whatever the samples you are getting, actually it is producing through IID assumption, right? That means identically distributed and independent things, right? So here in this case, what will be the likelihood if I'm saying that P is my parameter probability of success? Then the likelihood will be P into 1 minus P into 1 minus P into P into P into 1 minus P into P into P, like that, right? So this I'm just talking about, right? If I'm assuming, and then we differentiate on, and that entire likelihood will be a function of parameter P, and then we differentiate that P with respect to differentiate that function with respect to parameter P, and then we equate it to 0, right, to find out its estimate, right? That is one of the techniques in which is called as a maximum likelihood technique, right? So what is this symbol represents? L of P. So given this sample, right, given x1 x2 to xn, what is the uh, parameter P, or in this case, what is the probability of success P here, right? And that's how it is solved. So this is called as the argument that we are maximizing this product with respect to P. Fine. And why we use log? Because
To simplify.
differentiating that product is
Uh,
difficult,
Differentiation of logarithm is easy, I
easier,
think.
because yeah, it will flatten out its product, and we'll get that.
When things become very complicated, then it becomes easier to
Yeah,
differentiate.
product, yeah, differentiating product will be difficult. Why it is difficult, you can understand, right?
Yes,
So
sir.
suppose you x square into sin x, if I wanted to differentiate that part, it
UV
will
rule
be,
is applied.
yeah, we have to use that product rule, right? U into v, and then the things will become complex. So if you have that logarithmic with that, so it will become like sum of, right? So that product will we can look at it into sum, and then we, so basically what we do, we'll take a log of likelihood, right, and then differentiate with respect to that parameter. In general scenarios, whatever sample we are getting, right, we assume that that sample is coming from a Gaussian
Gaussian mixture.
distribution, right? Because most of the real life scenarios, whatever data it's generated, right, it is coming as, like, for example, height of the students in a class or anywhere, right? So that will actually fit your, or marks of the students in a class, they should always fit into Gaussian distribution. So that is our primary assumption, that okay, this is the this is coming from the Gaussian, and this is the sample from the Gaussian, and now let me know what are the parameters for that, right? And
Yes,
that these are the estimates. They may not be the actual uh, parameters, right? They are
yes,
the
sir.
estimates, and that's why we call them as, like, we denote it by using hat,
P
right?
dash. Sorry, hat.
Hat. So mu ml hat is the. I hope this is, until this part everyone is on the same
Yes,
page,
sir.
right? But
Yes, sir.
yeah, but there is a possibility that we know. So let us say if somebody is working into a company, right, and they have the prior experience on, let's say, company which produces some nut bolts, right? So that person will have, so throughout the years, right, that person might have gained the experience about what should be its diameter, right? So because the diameter of that, let's say, nut bolt, right, nut or bolt, right? So maybe whatever bolt, so it may not be perfectly whatever it is said, right? It might be increasing a little bit, or sometimes it will be, so that tolerance will be always there. So if the tolerance is there, because that person knows it has, like, it might have that, uh, some information about the parameter, and that information is called as a prior distribution.
Prior distribution.
That is the information gained through the experience, or through the understanding of the people, and we use that to solve the maximum likelihood problem. Generally, we know that there is a base. What is a base theorem? Probability of A given B is, or maybe it's a conditional probability, right? So basically, probability of A given B is this one, right? How this comes, right? All of you know that.
Uh,
Yes, sir.
Yes, sir.
from total probability theorem, I think.
Yeah, total probability theorem. No, but like almost like kind of like that, but it's coming from the conditional distribution, right? So
Sorry.
probability of
Yes,
A
sir.
given B is basically probability of A intersection B divided by probability of B, right?
Probability of
And
B.
probability of B intersection A is probability of A intersection B divided by probability of A.
Mm-hmm.
So probability of A intersection B is common in both the cases. So we just equate these two statements, and from there
And
it is
this is probability of A given B.
right. No,
Yes, sir.
that's fine. So in this case, what changes here? So this probability of B basically, it is constant, right? It is a normalized way of doing it. So we just try to find it out. Probability of A given B, which is proportional to probability
Probability
of B
B
given
given
A.
B into probability of
Okay.
A.
But this probability of B given A in our case, parameter estimation case, it is a likelihood function, right?
Yes.
It's a likelihood. So and probability of A is the prior probability.
Mm.
Okay, so what we are doing is we are actually uh, taking a product of that likelihood function and that.
And sir, this sorry, sir. This probability of A given B becomes the posterior distribution. Posterior, no, I
Yeah,
think.
this will be a posterior. Probability
Uh,
of A given B is a posterior. So posterior is directly proportional to its likelihood and
likelihood and prior.
prior. But prior, just remember that the prior is a function of that parameter.
That parameter.
Okay,
Yes.
and likelihood also is a function of parameter, but
Function of parameter.
and this also is a function of parameter, and then only we'll find out its distribution later on. Fine.
Yes, sir.
So I think at least these tools, they are there. So here I think if you have gone through all of this is uh, that we have already seen in the stats, right part, like maybe stats store.
It starts to
Yeah. So you just right, this one, this part,
likelihood into, yes, sir. I know.
likelihood
Yes,
into
sir.
prior. Everyone is fine with that.
Yes, sir.
Yes, sir.
And you see this prior is a function of uh, p, likelihood is also a function of p, and after that we'll try to see that okay, what is the posterior
This will
distribution,
come out as beta. Yes, sir.
beta distribution, right? Okay. uh, Fine, I guess. Then this is it for MLE. Now we know the all of these things, so we'll try to see how to use that for our
Clustering
EM
part.
algorithm. Yeah. So we have already seen in k-means clustering how you cluster this data, or why,
Based on the means.
based on their means. So suppose you have clustered those data based on the means, but now the thing is, what we are saying is this data, maybe so if let's say you have this kind of data here, right? So we know that there are already three clusters we can see already, right?
Yes, sir.
Uh, but let us say you have given the data, and you with this sample you wanted to say something about that sample. So what is our general take on the sample? Any sample, it might be coming from our Gaussian distribution, right?
Yes, sir.
So so if I try to fit this Gaussian distribution to this, it will give me some parameters, right? With the the thing is, here there is a problem here, right? Why?
Sorry, sir. Can you come again? I think we missed you
Am I
from
audible
here.
now?
You are audible, but I think there was some from here. That cluster part after that.
Okay, clusters. Okay, leave about it clustering for now. Let us
Yes,
say,
sir.
okay, think about this part. You have this data points given to me, right? Okay, these are
Yes, sir.
some data points given to me. Now I wanted to, or data points in the sense you are given some samples to you, right? And now you wanted to find out what is its underlying distribution, right? what distribution this data comes from, if that is my goal to know, right? So generally, in general, what we say is we say that this data might be coming from your
Gaussian.
Gaussian distribution. And if I try to fit the Gaussian distribution, and I'll get this parameters, right? So mu hat ml is I'm
Get
getting it
some
from
parameter.
likelihood
Like,
estimate. But the important thing to notice about this is, even though I am getting these parameters, but if you see that these data points right here at the ends, the probability with this distribution, with mu hat ml and sigma square, the probabilities associated with this data points, right,
yes,
it's
sir.
very low,
Yes.
right? So then that means it's not a good model
Good
for this
modeling.
this kind of distribution, right?
Yes, sir.
Even if it is giving, because see, maximum likelihood is anyway a tool, right? Or maybe a mathematical tool to get, so you will get some mu hat ml, and you'll get it, and you can see from this data itself where this
Sir,
uh,
may I something?
yeah, mean will lie, yeah.
Uh, yes, you said that here in the downside, the probability is coming very. I mean, mu ml is very low, so that is why this modeling may not be good.
No, 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 no,
So,
no, no, no. It's not like that. See, okay, I'll tell you one. Okay, I'll try to again go slow.
okay.
So let us say you have this data points, right, above.
Yes, sir.
Okay, I'm just assuming that there is a distribution like this, the Gaussian distribution,
Okay.
and you can understand like, visually also you can see that the mu, right, the mean here, the mean is actually will be somewhere here, right?
Centered here, huh?
Right, and about this mean, the your distribution will go around, right? So fine. So if I try to fit this distribution to this data, fit, right, we are fitting this distribution to this data, and we are trying to fit the distribution of, let's say, Gaussian distribution, right?
Okay.
Okay, in that case, what is the problem here?
The problem is, I think the problem these mu estimation
The
problem
probability
this
for
side is
one
coming very low.
cluster is very
Yeah,
high and
so
other two is very low.
Unevenness in the probability, I think.
unevenness, or maybe see, it's not see, even though there is a very high chance that see, it's a generative story, right? So we are actually generating some samples from the population. So there is like maybe higher chance to get a next sample from this also, right?
Yes,
Or
sir.
this, or also, like, let's say you have got like 10th data point here. I'm having 9 data points. If you can actually see that there is what is the chance that I'm getting another data point from this. Suppose if I want a new data point, or new sample out of it, if it comes from this point, this part, right, it will have
Yes, sir.
high probabilities. And if it comes from this part or this part,
It will be having very low probability.
low probability, that means we are ending up actually clustering it into which one. If this comes from there, we will actually assign that to this part, right, instead of
Sir, your audio, sir.
my audio is having issues.
Of noise coming from someone's microphone.
Yeah, Vishal, if you could mute yourself.
Okay, yeah, so fine, right? So is this fine now? I'm not sure.
Yes, sir.
Yeah. So here you have to understand one thing is, we need some other distribution, right, to to explain this data, maybe, right? Correct. So even any sample, if I'm drawing it from this data, I should be able to correctly assign the probabilities to that, so that I can be my model, like whatever I'm modeling here about these data points, it should be modeled into good uh, you know good generative story, probably, right? So let us say, uh, if I try to do this thing, right? So this is called as I think all of you know that this is a Gaussian mixture model, right? So why it is called Gaussian mixture model? What we are saying that each of these clusters here, right, each of this is coming from one Gaussian distribution, and now we are connecting all of these Gaussian distributions together, and now we are saying that, okay, now if you see, right, if I get some data point from here, it will also have a good chance that it will be coming from this. So suppose if some data point is here, let us say here, right, where my cursor is. So ideally it should be going into this cluster, right, instead of this, correct? But previously if I think about this point, it will be having very less probabilities, and it will not, it might not go into that side of cluster, right? But now this kind of, so now this is a good fit for our data, right? So how to do that, like how to get all of these things done, right? Or now we can say that there will be three distributions, three in the sense, I'm just saying that here by looking at this data, there are, let's say, three distributions. One of the distributions will have, so now we are assuming that all of these distributions are Gaussian distributions, and now each of these distributions, so you know, right, how many parameters are there for any Gaussian or normal distribution? Two
Two
parameters.
parameters.
One is the mean,
Mu,
and another is the sigma square or variance.
sigma, variance.
So if I assume that there are multiple Gaussian models, that means, let's say in this case there are three, that means I will have how many parameters? Six parameters, right? But we have to say that, okay, that we have to assign, since it is a mixture model, right? So it's like we are actually saying that, okay, there are three Gaussian distributions. So what is the chance that that data comes from which distribution, right? So let's say this is one distribution, this is another second, and this is third. So what is the probability that uh, that data point comes from the first distribution? So we should assign some probabilities to each of that, and you see that each of that, let's say, and that is denoted by, let's say, pi, right? So the pi 1 plus pi 2 plus pi 3, that probability will also be equal to, that it should be equal to 1. Okay, is that fine?
Yes, sir.
Yes, sir.
Okay, so I hope this, until this part is clear. So now we have two parameters for each of this distribution, and one more extra parameter to get that we wanted to see, right? Let's say there are three different distributions, that means each of will have, what is the probability that it will comes from, let's just say in this term, try to understand, it is coming from first cluster, right? What is the probability that, the data point comes from the second cluster, or what is the probability that it comes from the third cluster, and so on. So these probabilities will be denoted by, let's say, pi, right? So pi 1, pi 2, and pi 3, and the sum of all of these pi's should be equal to 1. So now the question is, let us say you have got a new data point. So what is the probability? First thing you have to ask is, what is the probability that it comes from the first cluster, right? And now if it is coming from this first cluster, then what are their parameters, right? Right, again, you understand, right? So the parameters will denote you, will give you the probabilities. So this mu1 and sigma1 will give you the probabilities of that part. So it's kind of a discrete continuous case, right? There are two random variables, one is a continuous random variable and another is discrete random variable. So let us say x is a discrete random variable and y is a continuous random variable. So y depends on what? X. So given that x equal to 1, so given that x equal to 1, what is the probability that y happens, right? So y is basically a normal distribution. Given that x equal to 1 means it is coming from the cluster 1, and what is the probability in that case? You have no, you know that part, right? Or did you forget this part? I don't. Do you remember that part? The continuous plus
Which, sir?
the stats 2 part, the discrete and continuous case.
Uh, yes, sir. Discrete and continuous. Yes, sir. It's just
Okay, I'll just revise it a little bit. So
Yes,
here,
sure, sir.
yeah, what I'm saying is there is a random variable, x is a random variable, okay, and it is a, let's say it is a discrete random variable, discrete random variable, which takes values 1, 2, Okay, what is k here? Number of clusters, right? And y is what? Y is a continuous random variable, right? I'm just saying that. So given that given that xi, right? What is the probability that y? So let us say what the distribution. Okay, maybe I'll just show you the distribution. It will be normal, maybe mu1 sigma 1 square, right? Y1 given x1, right? So y2 given maybe x2, or y2, not y, is some normal mu2
Nothing
sigma
is
square
normal.
to square. So what is this representing it to me? If what is the now, so if I know this distribution, then I am sure that I'm able to find out its probabilities, right? So if I wanted to say that if any new data point comes, right, where what is the probability related to that? So first of all, the probability is associated with this, right? And that means if I wanted to find the probability, what is the probability of y here? Probability of y given x1 into probability of x1, right? Right?
Yes, sir.
Plus probability of, let's say, y given x2
Next to
into probability of
probability of x.
x2, right? Is that fine?
Yes, sir.
And how,
Yes, sir.
and why, how can we find out these probabilities? Since it's a discrete random variable, we know the probability of mass function there, right?
Probability mass function.
Yeah, so what I'm saying is they think this as, let's say, pi k, right? These probabilities, fine. So what is pi k here? Then, like, which cluster it is coming from, right? So pi k1 or something, whatever the things are there, and this you know already. So let us say, okay, in this case now,
Sir, pi k represents the probability of data point from which it is coming.
it's cluster, right?
Ah,
So right,
okay.
so this, let's say, pi k equal to, I don't know, what
Two, let's say two.
2 means it's coming from the second cluster.
Second cluster.
So that probability will be assigned to that, right? So I know what is the summation of all pi k's.
One.
1. So let us say first cluster is having probability 0.4, second is having 0.3, the third will be having how much?
Point
Point
four,
1,
seven.
point
1
three,
minus 7, 1 minus 0.7, right? Which is 0.3,
point three.
right? So let us say pi 1, pi 2 to pi 3. So how many parameters I need to see? Again, I don't know, right? Exactly how we have to define that parameter also, right? So how
Yes, sir.
many parameters you need to define for that?
For three, up to three.
Three, or okay, let's
Okay,
say
for
three.
three, I think two we need.
Two,
Two is
right?
sufficient
Because
because one
be-
can, we can get from
yeah,
minus one.
and for each of that clusters, how many?
K minus one.
2, right? No, that is k minus 1. That is okay. Okay, k minus 1. That those parameters, and each of that pi k again, or cluster 1, will have that Gaussian distribution, right?
Yes, sir.
So for that also two parameters. So that is
So it
2k
becomes,
parameters. 2k parameters, right?
yes, sir.
So 2k parameters plus k minus 1 parameters. That
So it
total
becomes
parameter.
3k minus 1.
Yeah. So I think somewhere it is there, right? This one. Now I hope you understand this part until this part.
Yes, sir. Yes, sir.
Why we
Sir,
need
Yes, sir.
how do we get k minus one? Uh,
see, we know those pi k is what? This probability, right?
yes,
From which
sir.
cluster? So let us say we have three clusters here, and what is the assumption we are saying? That, like, summation of all of this will be equal to 1, right? Because it's a probability mass function, right? It's a
Yeah.
discrete random variable. We know that there are, let's say, k what, k clusters,
K
suppose.
cluster.
So k clusters, if I know, and each of the cluster will have assigned some probability, right? Then let us say it is theta or something like that. So if you know all, or if you know each of that, not theta, maybe let's say, if you know that the summation of all of this should be equal to 1, in that case, if I know the k minus 1 parameters, the remaining one I can definitely find by 1 minus all of that,
1
right?
minus all of them.
Okay, right.
Right. So
Single
yeah,
probability.
so
Probability.
I don't need that last one's parameter, because if I know all others, that should be definitely equal to 1 minus all that, right?
Yes, sir.
That is k minus 1, and each of this cluster we are assuming that it is coming from Gaussian distribution. So Gaussian distributions each will have 2 parameters. So if I have k clusters, how many parameters it will have? 2k,
2K.
and 2k plus k minus 1. So
So
basically
it
it is
becomes 3k minus 1.
3k minus 1. Is that okay now?
Yes, sir.
Yes, sir.
Now what? Okay, so that means I need to find out 3k minus 1 parameters, right? Or find out in the sense we have to find the estimates for all of these, right? Which parameters I need to find it out? Estimates pi 1, pi 2 to pi k, and pi k
Up
means
to
like pi
pi.
k minus 1, and each of that mu k 1 sigma k square 1 mu k 2 sigma k square 2, like that, right? Right, this is okay.
Yes, sir.
This part
Yes,
is
sir.
fine. What is sigma pi 1, pi 2, pi 3? Okay, pi k up to pi k. Okay, fine, that is also fine. So how to do that now, right? That is a question we have to ask. So what is the likelihood, maximum likelihood method?
Product of the mixture function.
So you know this one, right? Pi k into this density. Is that fine? I have shown you already by writing it, right? That's fine, right?
Yes, sir.
Will that be okay, na? This uh, this density you understood, right? I
They are
hope so.
representing in the compact form, I think.
Yeah, it's understood.
Okay, so if it is done, then that, but still, if you just now, okay, I will not go through all the details again. You didn't took the log likelihood and all, right? All of these things will be there. But then again, it is very difficult, right, to solve this kind of problem, because it will involve like lot of calculations and all. So it, even we are using log here, still it is a hard problem to solve,
Very hard to
right?
solve.
Because again here the product involves, right? Even after the logarithm, it is not going away.
We have double summation and also the
So convex functions, all of you know about it. Vishal, I think you should go
sorry,
somewhere
sir.
the quiet place, right? It's we lot of noise is coming, so that's all. Yeah, uh, all of you know these convex functions. Is there any
Yes, sir.
convex function is so this
Yes,
is a
sir.
definition of it, right? F of function of a plus b by 2, it should be less than or equal to f of a plus, that's fine. I think if it's not like only f of a plus b2, it can work for any lambda, right, over that line.
Yes, sir.
So I don't think that's a problem there. Concave is exactly opposite to that, right? Now convex is, if it is less than or equal to, then concave is uh, at that point the function's value is always greater than the uh, that point which is on the line of line joining this f of a and f of b, right? So that is what definition of concave functions. Then uh, like if you see this calculations, we are just using the convex things right here. So I hope you know this part, this lambda 1 minus lambda, we have already seen in MLF, maybe. I don't know how many of you seen it, but still it's not that difficult. Whatever the whatever we have seen it for the convex function, we are actually using it for concave function. But how to use that? Instead of less than or equal to, it will become greater than equal to, right? Okay,
Yes, sir.
and now this is called as the Jensen's inequality.
Equality.
Okay, but that means this lambda k will be what, that lambda 1 lambda 2 plus lambda k, the summation should be equal to 1, right? That also we know. I hope all of you know that. If not,
Summation should be 1 and must be between 0 and 1.
0 1 and 1, yeah, that is its property, otherwise it is not possible here, right? Again, okay, so now log is concave function, so we have to use, okay, that this was our problem, right? We have to solve log of summation of k equals to 1 to k pi k into this entire thing. So what we are doing is, to solve that part, we are just multiplying this by these lambdas. Okay, just we are just taking some lambda, right, to multiply that function. And if I am multiplying with that, that means I have to divide it by that
The
same
same.
same, right? Okay, now if, and the property of lambda is also that the sum should be equal to 1, and
1
each of this lambda should be between
between 0 and
0
1.
to 1. Okay. Pi k, what is the property of pi k? The summation of all
Summation of all of them must be 1.
should be 1. Yeah, now I think this is clear. So how we are going to use this instance inequality over that? We have said that log is a concave function. So log of this part, right, entire part, summation of k equals to 1 to k lambda k into this all this part. Now it can be written as so log can go inside here, fine. So
Yes, sir.
logarithm of all this thing into lambda k, and generally if you see that this should be equal greater than equal to this part, right? Now we are just saying that by using the instance inequality. How
What,
do
sorry, sir. What did you say?
okay, this quantity here which is written here, right, summation of
Yes,
I
sir.
equal to 1 k equals to k, this is actually is called as a modified log of L theta lambda, fine.
Yes, sir.
And this quantity will not be equal to log of L of theta, right? It should be less than or equal to log of L of
Yes,
theta.
sir.
What is log of L of theta? Which quantity is? What will be the left hand side?
Log likelihood.
Here, whatever we have seen here, no? This portion.
This thing.
Right now. So what we are saying is we are not going to get that exact log likelihood, but we are just modifying it, this log likelihood, by introducing some lambdas. But with that introduction of that lambdas, what happens to me, that will not become the equality, it will become
Lower
inequality.
bound.
And that inequality is coming from, since it is coming from Jensen's inequality, it is giving me the lower bound of that, right? What is the meaning of lower bound?
Means I think it cannot go below that.
Yeah, it is a minimum value, right? Whatever
Yes,
the
sir.
log likelihood value will be there, it is always, maybe it is greater than or equal to, but it will not be lesser than that this quantity, that's it. Okay. Now we have got this equation now in our uh, hand. So how to solve this now, right? Again, solving this again is the normal method now. What is the normal method to solve this? Now this function has
Take
become,
derivative.
yeah, now previously we had one the function which was a uh, which was the function of theta. Theta is basically everything, right? Pi k, mu 1, sigma
Yes, sir.
everything. Now we have introduced one more parameter which is lambda, and now we have to uh, we can actually use uh, so we can, if I wanted to take a derivative of this, I can take it with respect to theta and make lambda constant, or with respect to lambda and make theta constant, right?
Yes, sir.
So these are the two steps. And if I do first step, so fix lambda and maximize over theta, this will be this function. And okay, I think you will get this part, right? You will get mu k hat ml, right? So that will be uh, what you, okay, max over theta, right? Yeah. So what is this part? These are okay, these are the estimators, right, which we are actually using for solving the equations. We'll see how to solve that, but yeah. So you will get this mu k hat ml, and sigma hat yeah, maximum likelihood, or modified mml means modified maximum likelihood. Okay. So maybe okay, that part again we can solve. So this is, we are okay, I think we are getting rid of this pi k in this term. We are not actually, we are treating pi k constant, and then we are getting mu hat ml and sigma hat ml. But again, by solving for, by treating mu k and sigma k constant, we are actually solving for lambda k into log of pi k, right? This part is fine or no? So basically, for solving any problem, you have to know this mu k hat ml, sigma k hat ml, and pi k. But how we achieved that? What is the use of lambda k? You can understand the lambda k use is here. No.
No, sir.
Okay. So if Okay. Maybe we'll see the solution questions, and then maybe after, if you see the in the
Yes, sir.
numbers, right, maybe we'll be able to understand properly. We'll see the algorithm once more. What is this algorithm says to me? We initialize with something, right? Let us say we initialize with something, some theta. Thetas are what? Mu, sigma, and pi's, right?
Sigma and pi.
Okay. Our modified log likelihood is dependent on all these parameters theta and the lambdas, right? So lambda t plus 1 will be what? R max over lambda, right? And theta coming from the tth iteration, right? The previous iteration. Fine, no? Okay. Because we are treating lambda as constant. Sorry, we are treating theta as constant. So
Theta is constant.
we have to take that theta t from the previous iteration, and
Previous equation.
uh, we maximize over the lambda, and theta t plus 1 how we'll get, we'll treat lambda
Lambda
constant,
is constant.
and this lambda t plus 1 is from where we are getting,
Coming from
from
this
the above step,
up above one.
above step, right? And then this step is called as expectation step, the lambda t plus 1, and this step is called maximization step. That's why this algorithm is called expectation,
EMM.
yeah, maximization, right? We'll see the problems now, and then we'll try to see whatever we have. Let us see if we can stuck somewhere or not, right? This is the overall idea. I just gone through like very fast manner, but let us see, through examples might be easier for you. Okay, shall we see now?
Yes, sir.
Yes,
Yeah.
sir.
So I hope all of you will involve in solving this, because if you not, then you'll not be able to understand what is happening. Right? Okay. This is the first question. The PDF is given to you. Uh, f of x given lambda is this PDF, right? And then where k is some constant and lambda is a parameter that we wanted to estimate using the maximum likelihood estimator. Choose the option which has the correct MLE from the MLE form of lambda. Yeah. How will you do that?
Take log.
First of all, take a product, right?
Then product, yes, sir.
Yeah. And then log. Okay. Yeah.
Sir, I think option B.
Yeah, solve it. Everybody is done. If you're done, then I will solve it. Okay. Let me see. Okay. I've written the answers. Yeah. Can you just write your answers in the chat box? It will be better so that I can understand. Like few of you have already solved, right? B. Okay. Option B. Option B. Okay. B. Everybody is B. Okay. I'll wait for one more bit and then we'll see. Okay. Maybe I'll solve. We'll see that solution itself. Okay. So first place we have to find out the likelihood function, which is so each of the samples, right? So xi will take different values here. So what it will be? K upon lambda xi by lambda to the power k minus 1 e to the power xi by lambda to the power k. So whatever the density function is there, you just have to take the product for n values, right? So the log likelihood function will be taking the log of all of this. So you just see that log of product, right? So k by lambda plus k minus 1. Because of this log, this term, the exponent will come to here. So k minus 1 log of xi upon lambda. Basically it is plus log of e to the power, right? So since it's e to the power something, it will again come as xi by lambda to the power k, and log of e is, since we are taking the natural log, so log of e will become 1. Now this is my term what to do with this logarithmic terms now? Uh, yeah.
Find the derivative.
Differentiate.
So yeah, differentiate we can do directly, or we know that log of k upon lambda is log k minus log lambda, right? So we'll just simplify it a little bit, right? So k minus I log of xi uh, minus, I think here there is a mistake here. So k minus I log of xi minus log k minus 1 log lambda, right? The k minus 1 should be, because it is multiplied to both, so it should be multiplied to both of these values, and here it's the same thing. And then take a summation along with that. So sum of I equal to 1 to n log k is, since log k is a constant, right? K is a constant, so it will be n log k. Similarly here, again log of lambda will also be that will be n minus n log lambda k minus 1 summation. So this will become summation of log of xi, because xi is I equal to 1 to n. And okay, so this is the expansion. I hope all of you have done that, and these terms get cancelled out. Next thing is, now this is the simplified version of this, right? So n log k minus kn log lambda plus k minus 1 log of xi minus summation of I equal to 1 to n xi by lambda to the power k. After simplification, what you have to do next? So this is the simplified version. After simplification, what we have to do? We have to take, or we have to differentiate that with respect to lambda, right? By treating all other things as constant. Even anyway, the k is constant. So by differentiation, you will get this minus k by n. Okay, so minus kn by lambda plus k by lambda to the power k plus 1 summation of I equal to 1 to n xi to the power k. And if you take, and we have to set it to 0, so after the simplification, we'll get lambda hat ml as 1 upon n summation of I equal to 1 to n xi to the power k to the power 1 by k. So this is what, uh, so option C, right? Or option B, sorry, option B. Option B is the correct answer. Okay, I hope all of you have got this same answer. I'll share the sheet slides with you anyway. You can just check your calculations later on. So this should be the correct answer.
So you will share it in the supplementary content.
Yeah, supplement under supplementary content, right? And I'll also attach to this our meeting link also. Fine.
Okay, sir.
Yeah. So try this next question, which is, suppose that y follows a binomial distribution with parameters n and p equal to theta. So that means like theta. So that the PMF of y given theta is n choose y, theta to the power y, and 1 minus theta to the power n minus y. For y ranging from 0 to n, suppose that the prior PDF of this parameter is beta alpha theta, that is this h of theta will be, so h of theta basically represents the prior year. We have to find out the posterior distribution for theta using the Bayesian estimation. Is that okay? How will you solve this problem? So you will find out the likelihood first, and then multiply that likelihood. So likelihood of this thing, you will multiply that likelihood with h of theta, which is a prior, and then try to see what is the posterior distribution. And from the posterior distribution, you know how to find out the estimator, right? Either it will be basically posterior mean will be a estimator for the theta. Okay, try it out. We'll see the solution after some time. Is it done? Are you solving? Okay. NCY beta alpha. Okay. What is NCY times beta alpha? Okay. Okay. Let us see then what is the case here. Shall you see the solution then? Possibly we'll see that. Okay. Right. So likelihood will be n choose y theta to the power y 1 minus theta to the power n minus y, right? Into this prior theta to the power. So prior is given as already given, right? So theta to the power alpha minus 1 and 1 minus theta to the power beta minus 1. What is this prior? It's a beta prior. Okay. Now, if I multiply all of this, what I'll get? So n choose y basically will become a constant, right? So we don't have to worry about it. Just have to worry about the thetas because the posterior will be a function of theta. So theta to the power y into theta to the power alpha minus 1, that will become theta to the power alpha plus y minus 1, and 1 minus theta to the power n minus y, and beta minus 1, that will become beta plus n minus y minus 1. And this is also a beta distribution, but what is the alpha and what is the beta in this case? So alpha beta will be alpha plus y, this portion, and beta will be beta plus n minus y, this portion. And what is the estimator? Estimator will be what is the posterior mean of the beta? It is alpha upon alpha plus beta, right?
Alpha plus y divided by alpha
No,
plus
no,
y
no.
plus beta.
Only for beta alpha beta. What is the you understand what I'm saying, right? If in this case, let us say in this case, what is the posterior mean?
Alpha plus beta.
Alpha,
Alpha divided by
alpha,
alpha plus beta.
Alpha divided by
yes,
alpha plus beta, right? And now here your alpha is alpha plus y and beta is beta plus n minus y. So your posterior mean will be alpha plus y
Alpha plus y
divided by
alpha plus y plus beta plus n minus n.
so basically alpha plus beta plus n, right? Y will get cancelled.
Yes.
So your alpha plus y divided by alpha plus beta plus n will be your
Yes. Yes.
posterior mean. That means it is a estimator for theta, right?
yes,
Theta is in this case is p, probability of success. Okay. I think that was not a part of this question, I guess, because it was asked to find out the posterior PDF. But if it was asked to find out what is the parameter estimator, right? That should be your posterior mean. Okay. This question is little bit tricky, but let us try to solve this. Consider a 1D data set as x equal to, so this is all these data points minus 3, minus 1, 1 and 3 with k equal to 3 mixture of Gaussian. Okay. Using expectation minimization algorithm, we try to estimate the mean and variance of Gaussian component. Suppose the output of each step in an iteration is, what is each step? The expectation step, right?
the second step that we had.
Yeah, this one, right? Here we get lambdas, right? The first one, correct? Are you able to see the screen?
Yes, sir.
This is expectation step and this is maximization step. Okay. So now coming back to this problem, here these are the values, and where each Rij entry, this is a matrix, right? It's each Rij entry corresponds to the probability of xi data points belongs to the component j, right? That is lambda ij, because it's a expectation thing, right? So expectation step. Let mu1 hat, mu2 hat, and mu3 hat be the updated mean in the maximization step, which is the second step. What is the mu1 hat, mu2 hat, and mu3 hat? That is the question. So first of all, you have to find out the values of B, C, and D here. A, B, C, D, and A, B, C, D here, and then you can. How to find out this A, B, C, D? So can you think of what is this K here? K is three clusters, right? Basically, or three mixtures of Gaussians. So this is relate all these values 0.3, B, C, and 0.1. These are related to four data points. These four data points. What are these values? 0.3, B, C, and 0.1. What are these values?
Gammas.
Lambda 1, 2,
Lambdas.
3, right? Because that is our expectation step. In expectation step, what we do, if you recall it, uh, we try to find out the lambda, right? By keeping other or by treating other parameters constant. Fine, now. So these are the lambdas corresponding to each of these data points, and this corresponds to the first column corresponds to first cluster, right? The second is for second, and the third is third one, right? And now we wanted to find out what are the mu hat, mu two, mu1 hat, mu2 hat, and mu3 hat. How to find out that? What will be mu1 hat? Okay, I'll show you that also. Okay, maybe where we have found out mu1 hat. So what is a mu1 hat, mu2 hat, or this ml hat? Lambda ki into xi divided by lambda ki, right? I hope now it's making sense somewhere. We are getting
Yes.
all the values of lambdas, and we are using that lambda values in the next step to find out the parameters, right? If you just see the algorithm once again, what we do in the t plus 1th iteration, we try to find out the lambdas, right? In that, so and that gives me here this matrix is basically these are the columns, right? So lambda 1, lambda 2, basically related to each cluster. And then what we do, we use these values to find out parameters, and these parameters are like I can find out this, right? So I can find out actually basically everything, right? Pi k, mu k, and sigma square k. But the question has asked here is mu k. If I wanted to find pi k, how do we do that? I just take the sum and divide it by that n. N is 4 number of data points, right? It makes sense now.
Yes, sir.
Yeah, then can you just find out what are this sum of all these estimators? Now it will not take much time. You just take like maybe 2 or 3 minutes, and then we'll see. Just write your answers in the chat box. Okay, is it done? It won't be summation of y. What is it? What won't be summation of y? It's not now, right? It's like previous one. Okay. 0.54 minus 0.54, 0.05. What is the sum? Final sum? So there maybe you can write your final sum there. Okay, I'll just give you, all of you, one more minute to solve that problem. Okay. Uh, all of you got the idea, right? At least what to do here. Can you just give some thumbs up, like it is possible? One only. Others? Okay. Two. Others are solving or just they're the silent people? Three. Okay. Four. Anyone else who's solving here? See, if you guys are not solving, then I may move ahead, right? Yeah, if you guys are solving, I'll give you time. I don't have any issues. But if you're not participating into this, then there is no point. Yeah, I'll give you 2 minutes. Okay, no issues. Yeah. Have your notes in front of you, okay? And you can use those notes also. See that. Is this done now? Okay, I hope it is done. Let us see the solution now.
Yes, sir.
Yeah. Basically, it's same. First of all, how to find out values of B and C? Because all the lambdas we know that the sum is equal to 1.
1.
So yeah, so here maybe in the first column we will not be able to do that. In the second column, how to find out the A? 0.5
Sir,
plus
0.3 plus a plus 0.5 will be 1, na? 0.3 plus a plus 0.5 will be 1.
it's along the, yeah, okay, fine. So in that first A will be, we can able to find A, right?
0.2.
Yeah, 0.2, correct. Sorry, along with the K, right? We have to sum it. Okay, and then A will be 0.2. What about B?
B
2
will be
plus 1,
0.
B will be 0. What about C? 0.25, 0.25, right? Na?
Yes,
And D
sir.
will be 0.5.
And D will be,
Point 5.
0.5.
okay. So this is how it will look. Now, what is mu k hat? It is basically uh, it's lambda ki into xi upon this one, right? So we have 4 points. So it will be, we just have to multiply with this all these points with each of the data point. We'll take a summation and divide it by those sum. So zero point 0.3 into minus. So this 0.3 comes from here, and minus 3 will be the first data point, which is x. So minus 3, right? Then we have 0 into minus 1, 0.25 into 1, and zero point 0.1 into 3 divided by the first column sum. So you can see that it will be coming at as minus 0.53, and similarly 0.04 will be mu2 hat and 0.2 will be mu3 hat. If you take the summation, the answer should be minus 0.29, right? Those who have solved somewhere, okay, Siddharth is right. Geeta, you rounded it off, or what is done? I don't know. Maybe some. Okay, those who have answered it, just cross check your calculations once more. You might find it correct answers. Okay, let's go for the next question, which is a GMM is used to model a data set with 3 components. For a given data point x equals to 6, the likelihood for each component are as follows. Okay, so given that z equal to 1, what is the probability of x? Like that, we are getting all these probabilities. The mixture probabilities for the components are 0.4, 0.3, and 0.3. So what are these probabilities representing here? Can you just tell me? Probability that x equals to x given z equals to 1 is what? Is it a
So the
continuous probability,
prior
or
discrete ones.
think about it once more?
So it's giving it
Given that,
specific points.
yeah, given that z equals to, no, it is given for x equal to 6, na?
Okay, okay, okay.
You understand
It's
now?
a
Yes.
From how, from where this 6 coming? So what is the probability that it is coming from? Z equals to 1 is a cluster indicator, right?
Yes, sir. Yes,
So
sir.
if it is
Yes.
coming from cluster 1, what is the probability of x? Basically, it's a probability calculated by using that PDF, Gaussian PDF, basically, right? Will that be fine? And the mixture probabilities for the components are 0.4, 0.3, and zero point 0.3. Which component is most likely to have generated the data point? It's very easy. You just have to find it out. Yeah. Take 2 or 3 minutes to understand this part, and then write your answer in the chat box. What will be the answers? Okay, okay. I think yeah, most of you have written the correct answer. It's like you just have to do the multiplications, right? Here, pi 1 into this probabilities, right? And divided by that. So the posterior probabilities will be pi k into this probabilities divided by sum total probability. So you don't need like sum also. You can just by finding out this component probability itself. This is the maximum one for the third cluster or third component, right? So that definitely gives me that highest probability here, and that's why it is most likely to this point x equal to 6, the data point x equals to 6 is most likely to go into the third cluster, right? I hope this is fine for all of you.
Sir, are these PYQs? Are these PYQs?
No, no, no. These are like prepared by our TAs. The questions prepared by
Okay,
TAs.
okay,
I don't think these are the
okay.
previous year questions. Okay. Yeah. Uh,
So can you show the step 2 of the
yeah.
question?
So basically, what you have given here is given that z equals to 1, right? That point x equal to 6 is coming from z equals to 1. What is the probability of that? Is 0.2. So we just have to multiply this, right? Pi k is that pi 1 is what?
So probability of Z equal to 1.
Probability of
Probability of
Probability
selecting
of selecting the
Z
that
first
equal to
cluster.
1.
cluster.
Yeah, probability of selecting the cluster 1. Pi 2 is probability of selecting cluster 2. So we just have to multiply the probability of, so once I selected this cluster point 4, then what is the probability that this data point will go into that cluster? That is basically the multiplication of that. So we have to multiply these probabilities and divided by this is like sum of all, right? 0.08 plus 0.09 and 0.15, and that comes out to be 0.32. So if you take this each of the probabilities will be, you don't need actually this step also, right? Because the denominator will be same in all the three cases, correct na? So given the data point x, what is the probability that it is coming from cluster 3 is having the highest probability, and hence uh, that is the probability, that is the most likely component where the data point will go on, right? Okay. A data set has n natural numbers. Okay, let's see the question 6. A data set has n natural numbers. If we assume a Poisson distribution with parameter lambda as a probabilistic model, what is the likelihood function and what is the maximum likelihood estimator of lambda? Do you need to solve this or shall we skip that and move ahead? If you want, you can solve it. It's like it's a recap of your stats too, right? You just have to find out the uh, likelihood function, and then I think most of you know, right? What is the Poisson distribution? Maximum likelihood estimator for lambda for Poisson distribution. If you don't know, if you will try it, you can try it and solve it. Okay, I will not maybe give you much time for this. Is it done? If it is not done, what are your queries? I don't know. If Sakshi is saying something, what are the queries? Okay. Maybe I'll go through it like once more, right? So, e to the power minus lambda, lambda to the power x upon x factorial. So the product will be what? E to the power minus lambda. So basically pi of that, right? It goes from 1 to n. E to the power minus lambda. So that will be like, it will be multiplying to each xi times, right? So it will be e to the power minus lambda into e to the power minus lambda. It will become e to the power n minus lambda here, uh, into lambda to the power xi, right? So that sum will be there. So lambda to the power x1 into x2 into x3, like that. But lambda to the power, you know this part, right? Or do I need to write it down? This portion you are able to understand, right? You can say yes, no, something. Am I audible?
Yes, yes, understood.
That's understandable, right? Okay, because we already have done that, so not. Yeah. Okay, so then if I take a log of all of this, what will happen then? This will be my first term, e to the power minus n lambda. Lambda to the power summation of xi's will be my second term, so that will become plus and minus of this part. uh, and you know that this is a function of the parameter lambda. So this part, the third one, will become anyway 0, right? If I differentiate it also, if you can keep it, you can keep it. Otherwise, you can discard that also for the calculation purpose. And if I differentiate this uh, log likelihood and equate it to 0, the first term will become minus n. The second term will be summation of I equal to 1 to n xi 1 upon lambda, and that should be equal to 0, and that means n lambda will be equal to summation of xi, and that means lambda equals to what? Summation of xi upon n, right? So this will be the answer. Is that fine? Yeah. So basically it is sum of all the data points. So it comes out to be as a sample mean, right? If you remember it, it's a sample mean. Okay. Question 6. You can take tell me along with this side itself. These are the graphs given to me. So f of x1 for first graph is f of x1 is this part, f of x2 is that part. Option B and C and D, right? So select the options which satisfies the following inequality for lambda 1, lambda 2, which corresponds to 0, 1. So lambda 1 plus lambda 2 equal to 1. That is what. Okay. So which one will? So this is for uh, convex function or concave function. This inequality,
Convex.
convex, right? So which of
Convex.
these graphs will
B.
give me the convex function?
B.
Second.
B.
Option B only, right?
Yeah.
Option D is concave. Option A and C, neither convex nor concave, right? Is that fine?
Yes, sir.
And that is our again answer to the second question also, right? Yeah, I think first two options satisfy the given inequality. Okay, that is okay, but the convex function will be only one. The option. I think this is also not a convex function, right? There is a mistake.
No, it is not convex.
Right. So I think there is a mistake in the solution possibly. I'm not sure about it. What is it? Okay, you can read it later on and I share that with you. Okay, this is the question number 7. Uh, we are trying to fit a GMM for this following data. At the teeth round of the EM algorithm, the following were observed. So these are lambda 3 is equals to all these points. So how many points are there in your data? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 points, and you will get 10 lambdas. Okay. The ith element of this vector represents uh, probability of zi equals to 3 given that xi. What will be mu 3 and pi 3 after the maximization step? This is what we have seen already in the previous question, right? It's like very similar to that. Only we don't have to worry about the first and second cluster. Is that correct? What will be mu 3? Summation of
Weighted mean.
lambda I into xi divided by summation of lambda. So that is your weighted mean. And what will be pi 3?
The average of the lambdas.
Yeah. So it's easier, right? Like take 2 minutes to solve this, and then I hope all of you like get a sense of it. What is happening here, right? I think so. Now you are able to understand the questions, right, and able to solve the questions, right? Okay. You can thumbs up in between so that I will be understanding that you may. Yeah. Thanks. Okay. It was 0.5, 0.32, 0.32, 0.2. Okay, got it. Okay, it's basically just like simple calculations. One is weighted mean and another is right. Okay, so yeah, this is fine. I guess this is 0.5 will be the answer, and 0.5 is the uh, estimator for mu 3, and 0.32 is estimator for pi 3. Is that right? That should be the correct answer. Okay, let's see the next question. Probably this is the last question. We have n IID samples from exponential distribution with lambda as parameter. Lambda is said to follow a gamma distribution with alpha and beta as parameters. Find the posterior distribution. Uh, is there any? Yeah, okay. So what is the prior distribution here for lambda? Prior distribution for lambda?
Gamma.
Gamma,
Gamma.
right? Yeah, and the PDF of gamma is given there. You don't have to worry about this part, right? Beta to the power alpha and that gamma function of alpha. You just have to take the only later part. Okay. Find the posterior mean for alpha equals to 6 and beta equals to 2, and the data points are given as like that. What is the posterior mean for Okay, you just find it out. Okay, I'll let you know. First of all, try to find out the posterior distribution first. How to find out posterior distribution? Likelihood into prior.
Prior.
Yeah.
Okay, done. Okay, okay, Shri, you can leave.
Please read my question. I've written in the chat
Yeah,
bar.
yeah, you can leave. You wanted what? Where to practice MLT coding too?
Where I can practice this MLT coding from basics because it's very new for me.
Okay. Okay, maybe you can post it on the Discourse. I'll try to answer there, right? Huh? Or
Okay.
maybe you can
Okay,
mail
sir.
it to me. I'll let you
Okay,
know.
sir.
Huh?
Okay,
Currently,
sir.
I have to look into this. I have books, but I have to look into books. So I'm
Okay.
just typing you my mail ID.
Yes, sir. Sir, like I have a good amount of time to give to this. That's why
Ah,
I'm
okay, okay.
asking.
Yeah, yeah. I'll suggest you.
Yes, sir. Thank
Yeah.
you.
Okay. Study.in. Okay. It's not typed properly. Just take that study.in.
Yes, sir.
Item.
Okay.
Ac.in. Yeah. Okay. So fine. Shall we see that the solution now? Basically, you just have to find out the likelihood, and the likelihood will be, since it's lambda e to the power minus lambda x, right? Likelihood will be what? Lambda to the power n e to the power minus lambda summation of x size. Prior is given as, so I said, right, you can use the later part only, and that can be, so this will be the multiplication of likelihood into prior. Then it will give me lambda to the power n plus alpha minus 1 and e to the power uh, this quantity summation of xi to like summation of I equals to 1 to n xi plus beta if I take minus lambda common. And this will look like what? Which distribution? Gamma distribution, right? And what are its parameters? N plus alpha will be your alpha of gamma, and this part, whatever the e to the power, this which is in the bracket, right? That will be your beta. And what is the posterior mean of gamma distribution? Alpha by beta. So that means n plus alpha divided by all this quantity, and that will be my posterior mean, right? So
So the prior is also a gamma here.
yeah, prior
Prior
also
is
gamma.
also
Yeah, it's a conjugate prior, right? So
okay.
prior was gamma and the posterior also gamma. So this prior is a conjugate prior, and then your posterior mean will become uh, 12 by 9, which is 1.333, right? I hope it is fine. The calculations is not an issue. The only thing is you just have to come up with this distribution, posterior distribution. Okay? Yeah. I think that's it from the slides today. I hope all of you understand how to utilize all of that what we have learned in the lectures, right? To solve the problems, and the problems will also be like more or similar kind of problems. So it will not be go very much outside of it. Fine. Okay then, guys. I'll share that slides with all of you. Maybe it will get updated in 1 or 2 days. For now, good night. Bye bye. So
Thank you so much,